Since we shot the previous videos in this lesson, a couple of things have happened that affect this course. First of all, the COVID-19 pandemic has swept the globe. So we have been self-isolating like many people around the world. As of late August 2020, the Vanderbilt campus is still closed to non-essential workers. Well, I'm sure you and I can agree that I'm absolutely essential. In fact, I don't know what I'd do without me. But it's not essential that I be on campus, or really that I be anywhere for that matter. So instead of coming to you from the campus studio, I'm coming to you from my home. The other thing that happened is that Akash and I have decided to add another topic to our original outline, error handling. So even though we told you that we have 3 topics to present in this lesson, and that the one on live scripts was the last one, here we are with a bonus 4th lecture. So good news, this course is even longer than you thought, and no extra charge. So why is error handling so important that we're adding it to the course? Well, you've been programming in MATLAB with us for weeks now, so you should have learned the value of the age-old saying, expect the unexpected. If your program works with data like the vast majority of programs do, the data that it gets may not adhere to the assumptions you made when you wrote your program. Or if you're using other people's functions in your program, they may not satisfy assumptions that you've made. And that's true for MATLAB's built-in functions too. And of course, while you're developing your program, you will make mistakes, and your program will behave in unexpected ways. All of these are sources of error. And if you want your program to be robust, which of course you do, it's very important that you handle these errors, and handle them well. So if error handling is so important, how come we didn't include it in the first place? Well, that was an error on our part, and we're handling it now. So far, we've dealt with errors in 2 ways. We've handled them one way when we're getting the bugs out of our program so that it'll work correctly, and a second way after the program is completed and someone runs it who doesn't know how it works. During debugging, when MATLAB gives us one of its dreaded red error messages, we've tried to determine the cause of the error from the message. Here's an example. It's a function called indexing, with an error in it that's so simple you might be able to see it before I even run it. It gets a vector of n random integers from Randy, then calculates the differences between successive elements of the vector and returns them to the caller. I'll let you take a few seconds to see if you can spot the issue. But while you're looking, I'll let you in on a little secret. After I've written a code segment, I usually don't spend much time trying to find bugs before I run it. For me, the best way to find them is to run it and see what happens. Okay, time's up. Here we go. Index exceeds the number of array elements, 10. Error in indexing line 6, and it shows the offending line. This one right here. In a simple case like this, MATLAB's error message is all we need to realize our mistake. When II equals the length of V in this for loop, which in this case is 10, VII plus 1 is asking for the 11th element in a 10-element list. The for loop should stop at length V minus 1 instead of length V. It's that simple. Let's fix that. Better save it and run it again. That's better. And this is a reasonable approach to error handling when we're debugging our program. But it may not be a good approach when our program is being used by people who are unfamiliar with the inner workings of the code. MATLAB's error message helped us because we understand the code. We eliminated the bug, but you can still cause it to fail by giving it a non-scalar or non-numeric input. In many cases, the user may inadvertently give a function input that causes an error, and MATLAB's generic error message, which would be adequate for the person who wrote the code, may not give the information that the user needs to understand what they've done wrong. And that's especially true with more complicated code that calls other functions and subfunctions and maybe indexes into multiple arrays. And by the way, people who are unfamiliar with the inner workings of the code just might include the person who wrote it, when that person runs it long after writing it and has forgotten what's going on under the hood. For that situation, we've dealt with errors in another way. We've tried to think of all potential errors that users might make and added code in our program to handle them. Remember how we made functions robust by checking the form of the input arguments to make sure that they satisfy the requirements for the function's calculation, and issuing explanatory error messages if the inputs are bad? Well, here's a function that does just that. It's called myHarmonic, and it's named that because I wrote it, and it calculates the nth term in the harmonic series, which is the sum of the inverses of the first n integers. The reason for the name harmonic for this series is interesting, but not interesting enough for me to talk about it. Of course, by now I'm pretty sure you've decided that my requirement for calling something interesting is a pretty low bar. But if you want to know why it's called the harmonic series, you'll need to Google it. Before this function starts into its computation of the harmonic sum, it checks to be sure that the input n is a positive integer. If it isn't, it calls MATLAB's built-in error function to chasten the naughty user that had the cheek to violate its input rules by printing a sanctimonious error message. The message is positive integer input expected, ... That ... That ... says a lot, doesn't it? It changes the message to something like this. You have clearly chosen to provide incorrect input. In the future, please have the decency to provide a positive integer. Let's run it. Error using myHarmonic, line 3, positive integer expected, ... And of course the error function prints its message in the command window in the dreaded red color, after which it shuts down the function entirely, refusing to budge until the user's behavior improves. You know, I used to love the color red, but now every last shred of affection I've had for it has been driven right out of me by MATLAB's red error messages. Of course, I could change the color in the Preferences section of the home ribbon. Let's try that. To something like, I don't know, green. Of course, then I'd start hating green. It's a real catch-22. Catch-22? Well, you know, you'll have to Google that one too. Lately, I've been thinking of switching it to black, but I'm going to wait on that until I'm done with this MOOC at least. Anyway, this red error message showed up because 0 isn't positive. Let's try a fractional input, which is not an integer, and a vector, which is not a scalar. All of these violations of the input requirements by the user cause the error function to quit the function that calls it and print its error message. And mind you, it doesn't quit just the function that calls it, it quits the entire program, no matter how deeply nested the call to the error function is. Here's an example to show that. This function is called harmonic chain, and it's called that because it sets up a chain of function calls that ends with a call of myHarmonic. Harmonic chain calls the subfunction subharmonic, which calls myHarmonic. It's hard to imagine a more useless example of MATLAB code than this, except that it demonstrates the stopping of a program when a function at the end of a chain of calls throws an error and lets us see the error message that shows up. We called harmonic chain with a value 2.3, which causes an error, and it called subharmonic with the same input, which called myHarmonic with the same input. The error function was called while myHarmonic was running, so we have a chain of function calls. Harmonic chain to subharmonic to myHarmonic, which throws the error. When the error was thrown, myHarmonic was on top of the activation record stack, and all this red stuff with some blue stuff sprinkled in tells us not only the error message that we gave to the error function, which is positive integer expected ... but it also tells us what line each function on the stack was executing when the error function was called. The greater than sign here tells us that the function subharmonic is contained in the harmonic chain M file. And all the redness tells us the entire program was killed. Well, what if I don't want a program to quit every time some function in it throws an error? For example, suppose the program has completed 2 hours of calculations, and just before it stores the results in a file, it calls myharmonic with 2.3 as input. I sure as shootin' don't want everything to stop before the results are saved. I might want to see an error message, but I don't want to lose 2 hours of calculations because of it. So how can we avoid having myharmonic stop the music when the user hits a sour note with bad input? Well, one thing we can do is change the way it checks its input so that instead of calling the error function, it just converts bad input into good input. Like this, for example. In myharmonic version 2, if the if statement detects a non-scalar, it picks off the first element. And if n is not a positive integer, this expression converts it into one. Let's try it on some bad input. 2.3 is a scalar, so the if statement did nothing, but it's not an integer, so the conversion statement rounded it to 2. And here, the if statement picked off the 2 to get a scalar from a vector. It works in both cases without an error, and as it happens, we get the same result for both calls because the converted input was 2 in each case. So instead of halting the program, giving a snarky error message, and possibly losing previously calculated results, it repairs the faulty input and drives on. I like the way it avoids an error, and it works well enough in this case, but there are problems with this approach. The first problem is that in some cases the approach of repairing faulty input can produce unanticipated outputs that can themselves cause an error in the caller. If, for example, the caller used as input a 2-element vector, like our 2,3 argument, it would likely expect the output to be a 2-element vector. In that case, the caller might try to access the second element of the output argument, which wouldn't exist. Thus, the caller would cause an error, which would stop the program. By the way, if you want to be cool, like I am, you're going to need to learn the cool way to say cause an error. You've heard me say it several times already. The cool way is to say throw an error. So in cool speak, I would have said, thus the caller would throw an error, which would stop the program. A second problem is that functions can fail in so many ways that we need to have too many statements to check for them. And in any case, it's doubtful that we could anticipate every one of them. And when one got through, the program would halt anyway. And a third problem is that when our function calls a function that we didn't write, for example, one of MATLAB's built-in functions, or uses a MATLAB operator, that function or that operator may throw an error and stop our program. All these problems can result in cases in which our program will halt when we want it to keep going, and it may print error messages that the user may not understand. Errors are going to happen. We have to live with them. But in some cases, the program halting and the red error messaging that goes with it can be worse than the error itself. Fortunately, there's a beautiful mechanism devised for exactly such cases. It's called exception handling, and it's available in MATLAB and most other modern computer languages. When we say exception handling, the word exception means an error that occurs in some part of a program, and exception handling means running code that is designated as being executed only when an exception occurs in that part of the program. Here's an example called robust harmonic chain, which I'm displaying next to harmonic chain. I've written robust harmonic chain because I've decided that I want to avoid the risk of having my program being stopped by my harmonic, which might have been written by someone else and might throw errors. To avoid that risk, I've produced robust harmonic chain by modifying harmonic chain so as to keep it from throwing an error when the call to my harmonic throws an error. To accomplish that, I've implemented exception handling by adding 4 lines. This line, before the call of my harmonic, with the single word try, which you can see is a keyword because it's blue. This line, after the call of my harmonic, with the single word catch, which is also a keyword. This line, in which the output argument h is set equal to the empty array, and a single line after that containing the keyword end. It's been a while since we've encountered a new keyword, and suddenly with exception handling we have 2 new ones, try and catch. The code from try through catch to end is a try-catch block, and it performs exception handling. The try-catch block is not special to MATLAB. It's also available in C++ and Java with exactly the same keywords. The lines try, catch, and end designate 2 subblocks of code. The try block, which runs from the try keyword all the way to the catch keyword, and the catch block, which runs from the catch keyword all the way to the end keyword. In this simple example, each block has just 1 line, but actually there's no limit on the number of lines you can have in there, or in any block in MATLAB, whether it's a try block, a catch block, or the body of an if statement, or a for loop, or whatever. As is typically the case, the try block calls the same function, my harmonic, that we called in harmonic chain, but here's the difference. If an error is thrown while my harmonic is executing, instead of halting the program, robust harmonic chain will run the code in the catch block, which in this case just sets h to the empty array. To use the terminology of exception handling, any error that occurs in the try block is an exception, and the running of the code in the catch block, which is executed only when an error occurs in the try block, is exception handling. Let's compare them on the same bad input. No red and no program termination. The only indication that something's wrong is the empty array as the return value. So the try-catch block solves all the problems we discussed by providing a mechanism to keep the program running no matter what bad thing happens inside that try block. An error that's thrown inside the try block is called an exception, and the alternative code that manages the issue in the catch block is the exception handler. As you can see, basic exception handling is easy to do, and the approach is elegant. And you can have lots of elegance too. You can put as many try-catch blocks in a given function as you want. And you can even nest them. With enough exception handling in place, you can be almost certain that whenever an error is thrown, instead of seeing red as your program grinds to a halt, you'll see the results of exception handling as your program drives on to get its job done. In more complicated cases, for example when it's not obvious from the return value that there was an issue, we may want to provide some sort of explicit message to the user that something was not quite right. We can print a message with fprintf, or we can use MATLAB's built-in warning function, which is similar to the error function in that it prints out a message along with its location in the code, but different from the error function in that it does not quit the program. Warning, wrong input provided. And here's information about where the problem happened. Notice that it says line 10 here because that's where the warning is. And instead of red, it's printing in this sort of orangish yellow. Red means stop, orangish yellow means caution. Now this is already pretty cool and super useful, but what if I only wanted to handle one kind of exception, or if I wanted to handle different exceptions differently? Of course, as I've pointed out before, you rocket scientists out there can deduce that there are bound to be good answers to these questions from the simple fact that I'm asking them. And you are right. As usual, we're going to demonstrate what to do with an example. First, let's set up a couple of matrices and multiply them. Was that fast enough for you? I initialized the random number generator and then used Randy to put a 5x4 matrix in X and a 4x6 matrix in Y. Their sizes are compatible with matrix multiplication of X times Y, so let's multiply them. And let's pretend that MATLAB has no built-in operator or function to perform matrix multiplication and implement our own function to do it. Boy, I would really miss that built-in matrix multiplication operator, I can tell you that. But let's pretend it's not there. And let's suppose that a MATLAB user is going to write their own matrix multiplication function and that they're going to use a helper function that we've provided for them. First, let's look at the helper function. This function is called element prod for element product, and it takes 5 input arguments. The first 2 are matrices, and the last 3 are scalars for indexing into the 2 matrices. R is the row index of X, N serves as both the column index of X and the row index of Y, and C is the column index of Y. The function performs a one-line calculation of the product of 2 elements of X and Y. As the comment explains, summing this product over the inner index, N, gives one element of the product of X and Y. And the user will do just that in the function to do matrix multiplication. Let's look at that function. It's called matmul for matrix multiplication. It takes 2 inputs, A and B, and it starts by doing some input checking to verify that A and B are matrices and that their sizes are compatible with matrix multiplication. Then it uses 3 nested for loops to calculate the elements of the output argument C, which is the product of A and B. The hard work is done by this line, which calls element prod, to calculate the product of the appropriate pair of elements of A and B. We could calculate the 2-element product right here inside matmul instead of calling a function to do it, but we put the product in a function to provide a good example of exception handling, as you'll see shortly. Of course, calling a function is a little less efficient, but we're not worried about efficiency right now. This can wait until our next lesson, in which we're going to spend a lot of time on efficiency. And as a matter of fact, we're going to look at a version of this very function with the 2-element product calculated inside matmul. Okay, suppose the user runs their matmul function using as inputs the matrices X and Y that we just created. Well, we've hit an error right away. But the message we get here is not from one of the 2 error functions in matmul. The input was good, so there was no reason to call them. As we can see from the error information printed in the command window, the error was thrown in element prod. But I happen to know that matmul actually caused the problem by mixing up the arguments in the function call. I know that because I set this problem up, not because of the error message. The message is a generic MATLAB one about array indexing. Index in position 2 exceeds array bounds, must not exceed 4. And I have to confess that I really don't like this message. Why, you ask? Well, it's just not informative enough. In particular, it doesn't tell us which array it's talking about. You can tell by what's shown in line 8 here that it's either X or Y. But which is it? X or Y? MATLAB could give us more information, but it's just not showing its cards. That would make sense if this were Texas Hold'em, but you want an error message to tell you everything it knows. MATLAB used to give a much better message, by the way. In the lecture on live scripts, you might remember me reminiscing about the great times I had with MATLAB 2014B. Oh my gosh, would you look at that? 2014B. That was a great vintage. I'll never forget it. And I made some great memories with that one. But live scripts weren't invented. Most of those great times were when Akash and I were making our first MOOC, Introduction to Programming with MATLAB. We made lots of errors, and old 2014B gave us great error messages. I got 2014B warmed up again, so let's look at the message we get when we run it on exactly the same code that 2020A just complained about. As you can see, I have the functions matmul and elementprod all ready to go. First off, let's define the same matrices x and y to use for arguments when we call matmul. Check it out. These are exactly the same random numbers that 2020A gives us. The random number generator hasn't changed in 6 years. And now let's feed x and y to matmul. And of course we get the same error. The first thing you notice is that it's all red. There's no blue. But the important difference is that its message tells us a lot more. Attempted to access x15 index out of bounds because size x equals 5, 4. That's a lot more helpful. It tells us the indices that were used, and it tells us x's dimensions. Man, they just don't make them like they used to. And the very next year, for some reason, the message was shortened to this: index exceeds matrix dimensions, with no hint about matrix name, indices, or sizes. MATLAB giveth and MATLAB taketh away. And it stayed like that for 3 long years before the message was expanded to what we have today, which is still not as good as that superfine message that we got from good old 2014B. I miss you, buddy. And this brings up another issue. Even when stopping the program is the right thing to do, the error message that's automatically produced may not be detailed enough. And the error message may change from one version of the language to the next. A changing message can be especially annoying if you're selling your program, because the error message can unexpectedly change if your customer updates the version of MATLAB that the code's running on. But don't despair. If you don't like the message that MATLAB gives you, you can generate your own message. Here's a version of elementprod that does just that. In version 2 of elementprod, we put the problematic part of our code inside a try block, and we put a call to error inside the catch block with a more informative error message. The program will still stop, but the user will get more information. One thing that might have caught your eye is the ME variable right after the catch keyword here. What is that? Well, when a variable is placed right after the catch keyword, then when an error is caught, that variable is assigned an object that contains information about the error, including the kind of error that was thrown, the message that would have been printed in the command window if the error had not been caught, and the state of the stack when the error was thrown. All that information is stored in the properties of the object. What's a property? What's an object? Hold on there. Patience, young grasshopper. We'll get to all that. You'll learn all about objects and their properties in Lesson 5, which is called Object-Oriented Programming. But for now, you can safely treat ME as if it were a struct with a set of fields. An identifier is the name of one of those fields. The identifier contains a string that tells us the kind of exception that was thrown, and we're accessing that property right here with the dot operator, just the way you would access the field of a struct. As you can see, we're using an if statement to determine whether the string in the identifier is the same as the string we have here, which is MATLAB : bad subscript. And if it is, we construct an error message and pass it to the error function. And how did I know that the correct identifier to check was MATLAB : bad subscript? Well, at this point, you might expect me to tell you where to find a list of possible exception identifiers. Nope, not going to do that. It's not because I don't want to, it's because I can't. And that's because you can't find a list like that. I've asked the MathWorks for the list more than once, but they tell me that although a list exists, they won't share it. Instead, if you want to find out what the identifier is for a given error, you should make the error, like we just did with element prod, for example, and then before you make another error, type this command in the command window. mException.last, where last means most recent. And up pops the information we need about the most recent error. At first I was cheesed off that they wouldn't give me a list, but after cooling down and thinking about it a while, I have to admit they're right. Throwing the error and then calling a function to get the information is actually a better approach, because a list of exception identifiers would also have to include a description of the actual error for each identifier on the list, so we could look those errors up. But what is the likelihood that our description would match their description? On the other hand, making the error amounts to giving a perfectly accurate description. And MATLAB has provided the mException.last command to give us all the information it has about the error we just made. mException itself is not a variable, it's a type of variable. It's the type of all variables like me in element prod that contain exception information. The command mException.last might look like a reference to a struct field or an object property, but last here is actually a special kind of function, which is called a method, that we will also learn about in Lesson 5, and it returns the most recent exception that was not caught by a catch block. And that is how I determine the identifier name MATLAB : bad subscript. Now getting back to version 2 of element prod. As I said, once we have determined that we are indeed dealing with an array indexing error, we generate a message with some useful information and call the error function with that message as input. Let's try it. Error using element prod accessed x15 and y51, but sizes equal x54 and y46. Basically, we have replaced the system error message with one that gives the user of our function more information to help in debugging. Now it's easy to see that there are actually two bugs here. The second index into x, which is 5, is too big because it's greater than the second dimension of x, which is 4. And the first index into y, which is also 5, is too big because it's greater than the first dimension of y, which is also 4. So this is the error message that version 2 of element prod gives the user who called it from matmul. There's no x or y in matmul, but the user can click this blue link to element prod and get the help message for that function. The explanation tells the user that x and y are the first input arguments, and since the first two arguments in matmul's call of element prod are a and b, the user knows that the problem involves indexing into those matrices. After reading the entire help message and thinking about it a bit, the user will realize that the problem is that the three indices used here, as the last three arguments in the call to element prod, are out of order. Instead of I, J, J, K, K, they should be I, K, K, J, J. Fixing that will solve the problem, but I'll let you try that yourself. I don't want to fix matmul until I've shown you a couple more examples that reveal more nifty features of exception handling. Before we leave this example, though, I want to point out a shortcoming with the error function messaging. The line number that it gives for the location of the error in element prod, which is line 15, is the line in the catch block where the error function was called, not the line in the try block in which the problem actually takes place. That information is available, though, in the property of ME named stack, and you can add code in the catch block to read that information and print it in the error message. We'll let you try that on your own, too. To show you the next nifty thing, I'll start by looking up the error that we just threw. Well, I see the error message that we gave, except for the fact that it shows a line feed character instead of feeding a new line. It's the message that we constructed. But if the user wants to see what kind of exception that occurred, he or she will be disappointed by the empty string here for the identifier. So what's going on here? Well, we caught the MATLAB : bad subscript error. So mException.last doesn't show that error because it shows only the information for the most recently uncaught error. The error described by this exception information was thrown inside the error function, right here. And that error function used an empty string as the identifier. Not a very useful identifier if you want to be able to distinguish one exception from another. Well, we can fix that by telling error to use a meaningful identifier string, one that we choose. And we can do that by calling the error function with an extra argument. We've done that in version 3 of element prod. The only new thing here is this extra argument to the call of the error function. It has to be the first argument, and it's the meaningful identifier we want. It's a string, and it must include at least one colon, and you can't put a space before or after the colon. I've included 2 colons so that I can identify all exceptions that my code throws with the leading JMF for John Michael Fitzpatrick, just like the MathWorks uses MATLAB, and I can identify this particular bad subscript as belonging to element prod. By the way, both the identifier and the message can be the old row vector of char type or the new string type. You know, single quotes or double quotes. They both work fine. Let's try this feature out. So we've thrown the error again. Let's see if it has an identifier this time. Yes, indeedy Bob. And it's the one we told the error function to use. So now we know how to set both the identifier and the message. Before we leave this identifier setting business, though, I want to show you another way to set it. And we're going to introduce a new built-in function to do it. This is version 4 of element prod, and it does exactly the same thing that version 3 did, but instead of calling the error function, it treats mException as a function that it calls to construct an exception object, which we've assigned to the variable mye. We give it the arguments for the identifier and the message. And then it calls a built-in function called throw with mye as its only argument. Aren't you glad I taught you to say throw an error? Yeah, because it fits right in with calling a function named throw to do it. Well, you're very welcome. So let's try it. Same thing, except that the line number in element prod is now 16 instead of 15 because that's where the throw function was called. We've used element prod to show how to accomplish our goal of handling a specific error. But are we done with element prod? Not quite. we're going to add one last nifty feature of exception handling to it. We're going to do that to solve a big problem with the way we've been handling exceptions in element prod. To see what the problem is, we'll cause an error to be thrown in element prod that's different from the bad subscript error, the one we've been catching. One way to make that happen is to call it with arrays in X and Y for which multiplication is illegal, even if we use perfectly good subscripts. Let's call it with cell arrays. First, I'll construct a couple of cell arrays in the command window. Now let's try to multiply a couple of their elements just to show that you can't do it. Operator asterisk is not supported for operands of type cell. No surprise there, we already knew that you can't multiply elements of cells. Now let's ask element prod to multiply the same elements of these same arrays. What happened to the error? Well, element prod caught it, checked the identifier to see whether it matched MATLAB bad subscript, found that it didn't, and so it just ignored it. Well, that's not good. At the very least, the user should be told that something went wrong, even if we want the program to drive on when errors other than bad subscript happen. Users should always be made aware of errors lurking in their code because they may cause big problems. So how can we fix it? Well, we add an else clause to our if statement. In that else clause, if we want to alert the user that a problem occurred but have the program drive on to avoid losing precious calculations, we can add an fprintf or warning function to tell the user that something bad happened. But if we want the program to behave just as it would normally behave when this error was thrown, we can reissue the error. In exception handling terminology, the error is thrown, we catch the error, and then we rethrow it. We rethrow it with a function designed to rethrow errors, and you'll never guess what that function is called. See if you can find it in version 5 of element prod. Time's up. It's right here in the promised else clause, and its name is rethrow. We call rethrow with the ME object that we caught up here with the catch statement, and it rethrows the error. Let's try it now. Operator asterisk is not supported for operands of type cell. So that's all there is to it. We changed how the array out of bounds error is handled to suit our needs, but we left every other potential error alone. And that's all there is to our element prod example. However, there's one more concept related to error handling that we want to introduce. It's called an assertion. One way to describe an assertion is that it's an assumption about variables in your code, and if that assumption is violated, MATLAB will let you know. Assertions are used while you're developing your program to help you exterminate bugs. Once you've tested your program thoroughly, you can remove the assertions or comment them out. Let's see an example. Let's say we have some long and complicated function. Along the way, we set a variable x that should be non-negative. We may be sure that it is, but if the assumption is important to the proper behavior of the code, we can introduce an assertion to be sure. In this example, we're sure that x is non-negative because we use the abs function to force it. But we add the line assert x greater than or equal to 0 to verify it. What does it do? Well, it checks its input argument, and if it's false, it throws an error. That protects us while we're debugging from proceeding on a false assumption and possibly doing a long calculation that's doomed from the start. In this example, I'm using both abs and assert to be sure of an assumption. I don't want to be caught with my pants down, so I'm using a belt and suspenders. I've been around the block a time or two, with my pants on, by the way, so I know that an extra line of code can be well worth the trouble of writing it. So is that it? Is that all assert does? We could double check it ourselves, right? Instead of using assert to throw an error if some condition is false, we could check the condition with an if statement and call the error function if it's false. So why would we use an assert function at all? Well, we'd use it to make it clear that it's not part of normal code execution. It's just helper code that we're using only during development. When development is over, it's easy to search for assert and remove or comment it out. And during development, when we look through our code, we know that X must be non-negative for a good result. And if it's not, we made a mistake in our code before the assert. The distinction might be a bit subtle, but I think you can appreciate it. In any case, let's get back to our example. How could X be negative at that assert statement? Well, one way would be that the code indicated by the do something more computation comment makes X negative. The assert function says that X should not be modified in a way that changes its non-negativeness. Or a typical rookie error would be if we reuse the name abs for our own function that does something other than what we expect. Let's run it and start by seeing what happens if everything is fine. Nothing happens, and that's what we want. We don't want to see any errors. Now let's create our own abs function inside assert example. And let's run the example again. And let's try it a couple more times. So, when we happen to get a negative value from our bad abs function over here, we catch the error because it violates the assertion. So whenever you say to yourself, I don't need to worry about this variable, I know it's a square matrix, famous last words, like, I'm sure the tiger cage is locked, or I'm sure this pool I'm about to dive in head first is deep enough. Well, a non-square matrix may be vicious, but it will not kill you. Still, put an assertion in your code and thank me later. Maybe it'll never throw an error, but if it does, you just saved yourself minutes, hours, or potentially days by immediately knowing that the cause of your mysterious error is that somehow that matrix turned out not to be square after all, or X turned out to be negative, even though you were absolutely sure about it. And with that, we'll wrap up this lecture on error handling. We began it by looking at ways that we've handled errors in the past, which were to use information from MATLAB's error messages to help us debug our code, and to use if statements to examine input to our functions for errors. We found that error messages from MATLAB are sometimes of limited value because they're not informative enough and can change from one version of MATLAB to another. And we found that detecting bad input is limited because there are so many kinds of error that writing code to detect all of them is just not feasible. To provide an improved method for dealing with errors, we introduced exception handling, in which errors in one portion of the code, which are called exceptions, cause another portion of code, which is called an exception handler, to run instead of generating MATLAB errors and halting the program. We showed how to implement exception handling with the try-catch block, which is delimited with two new keywords, try and catch. We then learned how to identify particular kinds of errors with an exception variable in the catch block and the command exception.last, and how to throw errors ourselves and rethrow them. And we looked at example code in which identifying kinds of errors and throwing and rethrowing errors helped us to write robust code. Finally, we introduced the assert function, which can help us during debugging to identify incorrect assumptions about the relationships among our variables. So we're done with this lecture, and we're done with Lesson 3. But I'll see you in Lesson 4. Or actually, you'll see me. Well, actually, you'll see and hear me. Well, there's a bit of a philosophical issue with that, though, isn't there? Because it's not really me that you'll see. It'll just be a moving image of me that you'll see. And it won't really be my voice that you'll hear.